Hello and welcome to today's lecture on circularly polarized microstrip antenna. In fact, in the last lecture we discussed about why we need circularly polarized antenna, and then we looked at simple configuration of square and circular microstrip antenna which can generate circular polarization by feeding at two orthogonal points. So, let us just continue our discussion. So, we had seen that here is a square patch and we had fed at two orthogonal points, and by feeding this one angle 0, one angle 90 degree, which is this is one angle 0, this is one angle 90, we got LHCP. Alternatively, if we make one angle 0, one angle minus 90, then it will become RHCP. Okay. And we had seen the component LHCP component and RHCP component, and we noticed that in the half power beamwidth ER component is very small, and then we had taken three different cases. So, epsilon r 2.55 with two different h and then epsilon r 1. So, what we notice that by increasing the substrate thickness and reducing epsilon r, we could get a much wider VSWR bandwidth. However, axial ratio becomes slightly poorer for epsilon r equal to 1 and h equal to 0.5, but still it is within AR less than 3 dB. Now, in this particular simulation we had assumed ideal condition of one angle 0 and one angle 90, whereas in practice it will never really happen. So, let us see today what is the practical way of realizing these configuration. So, here it is two different possibilities are shown over here. So, what we have here, this is a square patch and then a quarter wave transformer has been used. I will tell the reason also. So, we know that impedance is 0 over here and impedance is maximum. This impedance is much more than 50 ohm. So, it is a larger impedance. So, a quarter wave impedance transformer has been used over here, and similarly a quarter wave impedance transformer has been used here. Now, both feed 1 and 2 are never used. It is just to show you, if you feed at 1 you can get LHCP, or if you feed here you can get RHCP. Now, between the two feed the distance you can see is lambda by 4. Lambda by 4 gives us additional phase shift. Okay. So, if you see now this is symmetrical with respect to this here. So, you can say that the power going here will be equal to power going over here, but between this and this you can say distance wise the phase difference is 90 degree. So, by changing this position from here to here we can either have a leading or lagging phase shift which will give rise to LHCP or RHCP. But I generally do not recommend this particular configuration. I recommend this particular configuration, and even for this configuration we will show you some other single feed point configuration which gives actually similar response as compared to this here. So, I strongly recommend that please do not use this configuration. Okay. Now, this is a much better configuration than that. What is the difference here? This part is remain same here, and that is a lambda by 4 transformer is used here, lambda by 4 transformer is used here. So, this is a high impedance, that high impedance is transformed to 50 ohm here, 50 ohm here. Now, what we really have here, this is actually a 2 branch coupler. So, let me explain what is a 2 branch coupler. So, for that we have to first understand the microstrip line. So, think about if there is a one microstrip line here. So, if I feed at this particular point power will go to this end here, right, which is straightforward. So, now if I put another microstrip line which is in parallel with this line here with a small gap. So, what will happen now? There will be a microstrip line will have a some fringing field. So, that fringing field will get coupled to the other microstrip line. So, what will happen? Something field will get induced into it. So, think about if you have a current carrying conductor, then generally what happens? Induced EMF is in the opposite direction. So, here also if we feed in this direction, output mainly will go there, but part of the power will get coupled to this side, and this one theoretically is an isolated port, it will not get any power. Practically it may be minus 30 dB or minus 40 dB or more, depending upon the configuration which you have used. So, here we feed power, part of the power gets reflected back here, and generally this is used in many application. In fact, this is actually known as the coupled line directional coupler, and the coupling between the two is optimum when the length is equal to lambda by 4 or odd multiple of lambda by 4, then coupling is maximum. But the problem with this configuration is, even though coupling we say is very large, the coupling is still about maybe minus 6 dB, minus 10 dB or minus 20 dB. Now, that has application. For example, let us say if I am transmitting say 20 watt of power, and we want to really know whether is it exactly 20 watt or it is less or more. So, suppose we have designed a say 10 dB coupler, then 10 dB coupler would mean 10% power. So, that means out of that 20 watt, 2 watt will be getting coupled over here, but that is too high. So, that is why a 20 dB coupler would mean 1% power is coming here, and that can be used to monitor the power, or it may be used for automatic gain control, or this thing may be going to some other circuit. Now, that is a coupled line, but for circularly polarized antenna what we need? We need output which has equal amplitude. So, this is not going to do the job. So, to increase the coupling, now what you think about is that instead of having a gap between the two, if we now physically connect a line like this and physically connect a line like this. So, what we have achieved is two branches which are following from here to here and over here to here. That is what the configuration is known as. This is known as two branch line coupler. So, here is a one microstrip line, here is another microstrip line, and what you can see here, there are two branches are connected in between. Now, in this case, this length is lambda by 4, this is lambda by 4, this is lambda by 4, this is lambda by 4. So, let us just have a quick analysis in a very simple way. Suppose if I feed a power here, then part of the power will go here, part of the power will go to this side here, then this part of the power will go over here, and the rest of the part will go over here. Similarly, the power which is coming here, partly it will go there, partly it will come here. So, now let us see what happens. So, there are two paths from here to here. The two paths are one here which is let us say lambda by 4, lambda by 4. Now, each lambda by 4 gives phase difference of 90 degree. So, this is 90 and 90, 180 degree. This path also travels 90 degree, 90 degree, 180 degree. So, the two paths get added up. So, we get some power here. Now, for this particular port here, actually speaking, nothing comes here, that all depends how we choose the impedances. So, in this case what happens? The path over here gives us 90 degree phase difference, and then this is 90 degree, another 90, another 90. So, that is 270 degree. 270 degree is also equivalent to, you can say, minus 90 degree. So, this one here and this one here, these two cancel each other, and hence power is coming which is 0. Now, for this side here also you can see that the power goes here which is lambda by 4, which is 90 degree, from here to here to here, again it is going as 270 degree. So, then the question comes, why this is not becoming 0? The reason for that is we have taken a larger width here. So, larger width means larger power goes here, fraction of the power goes here. Out of this fraction power, some fraction is going, and then fraction of that is going. So, it is like this is also minus 90 degree phase delay, this here is minus 270 degree phase delay, which is plus 90 degree. So, even though the two paths have opposite phase, but cancellation does not. Think this way, suppose if this is coming out to be a, let us say a number, if we say 0.8, and if this is coming out to be let us say 0.1, so that will be 0.7. In fact, that is what is the S21 value here, but otherwise half power will be there corresponding to 0.707. So, basic idea is larger power is going. So, part of the power is only getting over here, which is subtracting. So, now between the two, what it is the phase difference between the two is 90 degree, which is what is required, and these impedances Z1 and Z2 are chosen such a way that half power goes here and half power goes here, and if half power goes here and there, that is known as a 3 dB 2 branch coupler. And just to tell you, so if this is a 50 ohm, then Z1 for 3 dB coupler comes out to be 50 by square root 2, which is 35.35 ohm. So these two are same, and Z2 comes out to be 50 ohm. So if we choose 50 ohm and 35.35, this becomes a 3 dB 2 branch line coupler. So now if we feed here, this will be relatively isolated port, or if we feed here, then this will be isolated port. So here we can do something interesting. If you feed here, let us say we will get a LHCP. If we feed here, then we will get RHCP. So when you feed here, this should be terminated with the 50 ohm match load, or if you feed here, then this should be terminated with 50 ohm match load. And now you can see that the power gets divided. If you are feeding here, half power here, half power here, which is getting impedance matched to this impedance, and hence it is properly matched and it gives circular polarization. Now the only problem with this particular configuration is it occupies lot of area, because already there is a patch over here which is lambda by 2 by lambda by 2, and we have a lambda by 4, another lambda by 4. So the size of the antenna becomes large. So that is the only disadvantage, but now this disadvantage we have used for advantage. We will show you the next configuration now. Now what is this configuration here? This configuration actually is circularly polarized suspended circular microstrip antenna with dual feed. So what we have done here, the entire green which is here, that is down here also, that is acting as a ground plane. So that is a circular ground plane which we have taken, and then we have a circular patch here which is printed underneath of this substrate over here, and that is suspended. Instead of in the air, we have actually used a foam to provide a proper support. Otherwise we can use air also, then you have to provide support over here. So this foam provides a support, and these two are substrates. So this we have used for this example RT Durite 5870 substrate, whose parameters are epsilon r h. We have taken a 0.8 mm thickness substrate. So these are the two identical substrates over here. So now the patch is suspended over here, okay, or printed in the underneath side of the substrate. Now what we have done, this 2 branch coupler that has been designed on this particular substrate here, okay. So this grayish color comes over here, you can see that is getting merged with this line over here, and then we are feeding at these two port here, port 1 or 2. So that is the port 1 corresponding to this over here, and this is the another port. So depending upon, again, we feed here or here, we can change LHCP to RHCP or RHCP to LHCP. So now these 2 points here are connected via this here. So you basically connect one, solder a wire here to here and solder another wire over here, and that is what the proper connection is. So in this case you can see that real state has increased in the vertical plane, but not in the horizontal as in the previous case here. And by using this configuration, we are actually getting a much broader bandwidth also, because effective dielectric constant seen by this is very small. Foam had a typical dielectric constant of 1.05, and this one had a epsilon r of 2.33, but since this is 4, this is only 0.8. Effective dielectric constant seen by this patch is just approximately around 1.1. So low epsilon r seen by the patch and also higher h, so which gives rise to the larger bandwidth. Now we will show you the actual design and requirement. So the requirement was, we wanted to have a circularly polarized antenna in the S band to cover 2.7 to 2.9 gigahertz, which is about 7% bandwidth. So that is why we chose this configuration. So, corresponding to this frequency and knowing what is the effective dielectric constant, patch diameter comes out to be 52 mm, a ground plane diameter is taken as 90 mm. Okay. So, this is the input impedance response corresponding to the feed port here. So, whether you feed at this port or this port, since everything is symmetrical, both the responses are identical. Now, let us just see what is the reflection coefficient response. So, here 0, -5, -10. So, instead of defining bandwidth for S11 less than -10, which would be very large bandwidth, we have actually defined it S11 less than -15 dB. So, even for this value, you can see that the bandwidth is from 2.62 to 3.1, which is 17%. Our desired requirement was only 7%. So, you can see that there is a lot of margin on both left side and right side, and S11 less than -15 dB corresponds to VSWR less than 1.5. So, it is a much better matched antenna. Now, corresponding to this here, let us see, this is the plot for axial ratio versus frequency. So, what we can see that this is the axial ratio 3 here. So, axial ratio less than 3 dB bandwidth is very large, that is about 21%, whereas our requirement is only about 7%. So, you can see that for that requirement from 2.7 to 2.9, axial ratio will be better than about 2.3 or so. So, it meets all the requirement as such, okay, for the desired design. So, let us just now look at the gain plot. So, for this particular case, gain is about 6.2 dB at the center frequency, and the gain variation over 2.7 to 2.9 is relatively very small. Here is the radiation pattern. So, LHCP radiation pattern at 2.8 gigahertz. So, this is the LHCP component, that is in phi equal to 0 and phi equal to 90 degree. You can see that, in fact, ideally if you take phi equal to 0, 10, 15, 20, full 360 degree, the variation should be relatively very small, and you can see that the variation is small, especially over the half power beam width range. We can see that the cross polar is slightly higher here. Here the cross polarized component is right hand circularly polarized component, but still that is about 17-18 dB below the normal thing. So, why cross polar is slightly poor? The reason for that is, again we can just see that the total height is quite significant and the feed is coming over here. These are the thing, and these will act like again a top loaded monopole antenna, and that will not be circularly polarized, that is a linearly polarized. So, this is getting superimposed on the radiation pattern of circularly polarized antenna, hence there is a slightly poor axial ratio. We are not getting close to 0 dB or 1 dB, it is close to 2, but yet we can see that axial ratio is less than even 2.3 dB over the desired band, and the isolation is still better than about 17 dB in the desired frequency range. Now, these are the situation which are for, you can say, the 2 feed antenna. Now, there are many configurations available. They actually use single feed circularly polarized microstrip antenna, and there are n number of variations are there for the circularly polarized microstrip antenna. Let me just say what these are. So, this is a nearly square microstrip antenna, where this is length L1 and this is length L2, and L1 is approximately equal to L2, but not same, and this is being fed along the diagonal. I will just explain this particular thing, how it is working. So, what happens, let us say if we feed along the diagonal, and we have to just take a case here. So, let us say L1 is larger than L2, but slightly larger than L2. So, what happens if L1 is larger than L2, that at lower frequency, which will correspond to F1, then this length will be resonant, and we are feeding it along diagonal. So, this length is resonant. So, that means there will be a phase difference of 45 degree. At slightly higher frequency, this length will be resonant because L2 is small. So, now this will act as a resonant. Now, between the two resonances, this is 45 degree and this is also 45 degree. So, between the two orthogonal resonances, phase difference will be 90 degree. So, that satisfies the criteria that the two orthogonal polarization should have a 90 degree phase difference. So, how that particular thing is achieved, that can be explained. So, let us just look at corresponding to L1, we will look at the resonance curves here. So, let us say corresponding to length L1, as I said length L1 is more. So, here is the resonance curve corresponding to L1, which is equal to F1. Now, corresponding to length L2, this is the resonance curve for F2. Now, you can see that if you look at this curve here, when this patch is resonant F1, corresponding resonator value of F2 is very, very small. So, this cannot give us a circularly polarization, because circular polarization has condition that the amplitude for the two orthogonal modes should be equal, and that condition is getting satisfied only at this particular point. So, at this particular point, which let me call now as F0, we get circular polarization. Why? At this point the two amplitudes are equal and also the phase difference between them is equal to 90 degree. Now, as the frequency increases, you can see here this amplitude is maximum, but corresponding to this amplitude is very, very small. So, for you can say 3 dB variation, let me use some different color. So, we can see that for 3 dB amplitude variation will be over this. So, this is the frequency range over which we can say axial ratio will be relatively less than 3 dB. Beyond that, axial ratio will not be very good. So, this is the general concept. So, just to repeat that and look at this particular configuration again. So, what we would like to see that at frequency F1 this length becomes resonant, at frequency F2 this length becomes resonant, and as I mentioned that at F1 when this is resonant, that will be dominant, E plane will be in this here, let us say horizontal, and at F2 the dominant will be vertical polarization, but in between as we change the frequency from F1 to F2, what we can see that dominant horizontal polarization changes to vertical polarization, but in between there is a circular polarization. So, this particular configuration as such gives larger bandwidth from impedance matching point of view, but it gives very small axial ratio bandwidth. So, now once you have understood this, you will actually see that these all configurations are very simple to understand. So, here it is a square patch, length L here, this is also length L here, but here this stub is attached. So, if by adding this stub what happened, this length will be slightly more than this length here. Okay. So, since the two lengths are approximately equal, slightly different, and it is fed along the diagonal, that means the phase difference between this and this will be 90 degree, and hence it can give circular polarization. So, instead of nearly square, we can use a square with two stub. Instead of adding stub, we can also cut a notch. By adding a notch again, what happens? This length will be changing through the path here, and this length will be changing through the another path. So, the two lengths should be different. Now, this is the configuration where diagonal is changed. You can see that a triangular segment has been removed from here and here. So, you look at this diagonal and then you look at this diagonal. So, you can see that the two diagonals have a different dimension, and between the two diagonals it is put the feed over here. So, for this feed, this will be let us say at 45 degree, this also will be at a 45 degree, one will be leading and one will be lagging, but the two diagonal will have a phase difference of 90 degree. Instead of cutting a triangular segment, we can also cut a notch like this. The concept is similar. So, again this length will be different than this length here. Then there is another possibility, that is we cut a slot like this here. So, now what happens, this diagonal length will be going like this and reaches here, whereas this diagonal length now will be going like this, going around and then coming back here. So, that means now the two diagonal lengths are different and we feed in between. So, this is minus 45 degree, this will be let us say plus 45 degree, between the two phase will be 90 degree. So, it will give circular polarization, but all of these configuration actually speaking give very less axial ratio bandwidth. In fact, we will see that typical axial ratio bandwidth obtained by these configuration may be 1 to 2%. So, let us just now take an example. So, here is an example where length is taken as 3 centimeter, which is L1, and what we are actually going to show you here, for different values of L2 what happens. Okay. So, here L1 is taken, feed point has been kept fixed as 0.15, L1 and L2, these are the substrate parameters. So, now let us see what we get for different values of L2. There are 3 cases are there, 2.9, 2.92, 2.95. I just want to mention here how to choose these particular values here. So, remember, corresponding to this here, since substrate is very thin, the bandwidth of this antenna is just about slightly less than 2%. First, let us just see the result, then we will come back to the ratio. So, for 2.9 you can see that there is a small loop over here. For 2.92, that loop has almost become a kink. In fact, the definition of the kink is when the loop size is almost close to 0, it becomes a kink. In fact, kink is the point which actually gives us the best axial ratio, because kink is the point where one resonance frequency is shifted to the another resonance frequency, and that is where the amplitude of the transition is exactly equal, leading rise to the kink. And if the value is increased to 2.95, which is getting close to 3 centimeter, you can see that the loop has completely disappeared. If this is equal to 3 centimeter, there will be no even bent also here, that will be going to the simple response will be of that of a square patch. Now, corresponding to this, let us first look at the axial ratio. So, we can see that the best axial ratio is obtained when there is a kink, and you can see that the axial ratio is relatively poor for other 2 cases. So, for optimization of these configuration, I always advise look at the Smith chart plot, and if it is a kink, that is what will give you the best axial ratio. Now, corresponding to these cases, this is the case for VSWR here. For the kink, this is the VSWR plot, and for the small loop here, this is the VSWR plot. You can see that this plot gives me a larger VSWR bandwidth, but that is not a useful bandwidth, because here then polarization changes as frequency changes. Since we have taken L2 as small, so that will have a higher resonance frequency. So, at lower frequency this will be resonant. So, let us say that will be horizontally polarized, and that at higher frequency then this will get excited, that will be vertically polarized. So, it will go from horizontally polarized to circularly polarized to vertically polarized antenna. So, VSWR large bandwidth is not useful, because in this case it will be horizontally polarized, then this will be linearly polarized. Only in this region we are getting circularly polarized, given by that axial ratio over here. So, this particular configuration gives us LHCP, left hand circular polarization. If we change the diagonal position, feed along this diagonal, that will give us right hand circular polarization. But even here, if we have taken L2 small, if you take L2 larger than L1, then for this feed it will be right hand circular polarization. Okay. So, it is important to know in which direction the field is moving, and that is what determines our left hand or right hand circular polarization. So, in the next lecture we will see many more configurations of circularly polarized antenna. We will also see how to realize compact circularly polarized antenna. We will also talk about broadband circularly polarized microstrip antenna. So, we are going to see lots of variations of circularly polarized microstrip antenna, and this material has been taken mostly from my book Broadband Microstrip Antenna chapter 8. So, see you. Please read this portion again before attending my next lecture. Thank you. Bye.